Next, our all-time favorite, the bell curve. Yeah. So the bell curve is often misunderstood. Bell curve is let's say it never occurs in real life, and also at the same time it always occurs in real life. Now why? Because when you say the height of all students in the universities follow a bell curve, follow a normal distribution with a mean of 1.6, standard deviation of 20 cm. That sounds reasonable, but also unreasonable, because you are also saying that there's a non-zero chance that some students, you know, if I randomly select one, there's a non-zero chance that the student is minus 50 meters tall. There's also a possibility, although very small possibility, that a student I randomly pick is 200 meters tall. Imagine that, right? Imagine that. How can we accept this kind of model? Hmm? Fortunately, the probability, the tail, is really so tiny that it may take all the atoms in the universe, right, or something like that, to even make it practically imaginably possible. So we're not going to worry too much about it, and then we will focus more on the benefits of why normal distribution is so applicable. Yeah. Okay. So there are definitely downsides to saying something is normally distributed, and those are the extremes here. Yeah. So the very extremely large and the extremely negative, they are all included whenever you say something follows normal distribution. So I just share with you this first. But what is nice is that whenever the measurements are known or expected to congregate at a particular value. Now, why do I say that? Some domain expertise or even the science tells us that these measurements ought to be concentrated around that value. Now, it can be artificial. For example, um, we are having a factory producing mobile phone screens, let's say, it's supposed to be by design 10 centimeters long, let's say the screen, right? But when you measure it very precisely to the third decimal place, micrometer, whatever, you might find that it fluctuates a lot. It goes long, short, long, short, long, short. Except when we look at it, we can't see with our naked eyes. Yeah, okay. And so within certain tolerances, where the customers can't tell, right? Then you kind of pass it and say QC passed, quality checked. But if you plot those uh, long shot screens, how many times did I see longer screens and shorter screens and all that? You'll find that it tends to follow normal distribution around 10 cm. So some of them are 9.9995 cm, some of them are 10.0002 cm, and so on. Yeah. So they're like just ever so slightly deviating either more or less from the standard spec design. That is what we mean by measurements are expected to congregate at a particular value, either by design, by human design, or by natural science design. For example, when we reach the age of 18 years old, we are all expected to be, let's say, on average, 1.65 meters, plus minus 15 centimeters, for one standard deviation. So SD, standard deviation of 15, 0.15 meters, average 1.65 meters. Why is that? Well, our DNA requires us to be so that we are not 3-meter tall giants. We are not 30 cm short, dwarfs. We are who we are, the height that we are because of DNA. So by design, again, we are all expected to be that average height, plus minus. Then, again, a very justifiable argument for choosing normal distribution to represent height will be, well, we all know we are expected to become of certain height. This is all common sense, common knowledge. So we should choose normal distribution and not uniform distribution. Right? So then the the argument, the knowledge, the domain expertise gives us this justification that using normal distribution to model the heights is a very good choice. So from there, when we derive probabilities, expected variance, standard deviation, and we make conclusions out of them, if they are reasonable, we say, see, it's supporting our action. If it's unreasonable, we got a shock and say, wow, then we better not do it, because we respect the fact that all our justification, our model, our choice of normal distribution, they're all correct. They're all supported by domain expertise, by science, by our understanding. And so if bizarre answers come out from this reasoning, we'll therefore say, well, let's better respect this bizarre answer and not try it. Let's avoid it. If, however, our initial choice of model, let's say we just choose uniform distribution, and we cannot defend the why. We say, why do you choose uniform distribution? I don't know, it seems easier. Okay, so we are unable to defend well the choice of uniform distribution. When we get some calculations, and we will be able to get some numbers, when it makes sense, we're not sure whether we can trust it. When it doesn't make sense, we're not sure if it's actually wrong because our model was wrong in the first place. So you see, there's really a futile exercise to choose an inappropriate distribution to match a given scenario. You see that? Yeah, okay. So a right choice of distribution is very, very important, so that whatever values we derive from there is going to help us either make the right decision or avoid dangerous or dubious, problematic actions. So when the measurements are expected to congregate around a particular value, then yes, we'll use normal distribution. The other case will be whenever we sum up large number of measurements, or we take the average of large number of measurements from any distribution, so long as they are identical, then the law of large numbers will take place. And this law of large numbers tells us that when you average out a large number of measurements, whether those original measurements follow exponential distribution, uniform distribution, so you just add them together and divide by the number of times you measure them, that average is going to follow normal distribution. So this is the very famous central limit theorem that we also talked about, right? So we'll see that again in lesson 4. Okay. The data behavior where mean and variance vary independently. And this is another peculiar area where normal distribution is very abnormal. And you may not see this so conspicuously because it's silently lurking around there. Okay, so let me just highlight it to you why this is a very powerful point for us to keep in mind. Notice that when we specify one of the normal distribution from the whole family of infinitely many normal distributions, we just need two numbers, the mean and the standard deviation. So they are just two separate numbers that we maybe estimate from real life situation and plug into this normal distribution family. Expected value is the number that we give. Variance of the normal distribution is the square of the standard deviation that we give. And of course, we can give them two numbers that are unrelated. For instance, you can have a low expected value, a normal distribution with a mean of 1, and a standard deviation of 10. Okay, so you are averaging around 1, but you are plus minus 10 or more, that kind of feel. Or you can have an expected value of 100 with plus minus 0.1. Right, just like the mobile phone's length. Yeah? So it is possible to have very totally varying mean and standard deviation. That might sound natural, but it's among the classes of distributions, abnormal is really not normal. Look at uniform here. When the mean value, when the b plus a over 2 is large, all right, when this value is large, variance is also affected by B and A in that relationship. So it will vary. When your mean is large, your variance has to vary a little bit. It need not be also large or small, but it will change. It's not totally independent. Look at exponential, even worse, because when 1 over lambda, when the mean is large, the variance will be large or will be larger. Remember, 1 over lambda can be a number larger than 1. All right, so when you square a number larger than 1, it will be larger. And when the mean is small, the variance is smaller. So they are very connected, right? They are not independent. And that goes for discrete case as well. That goes for other continuous distributions as well. So you see that over here, yeah, so they are all kind of related. This is not easy to see, but also related. Student T, little bit more bizarre, but it is closely related to normal distribution. So that's why there is a little bit of a separation there. But in general, normal distribution, not very normal in the sense that, and a good thing to us, in the sense that mean and standard deviation, they are independent. You can set them independently with no relationship to each other at all. Now, one last point is when the mean is 0 and standard deviation is 1, that's called the standard normal, the Z value, okay, the Z distribution. That's the basis of having all the Z tables that you probably have seen or have been told to print a copy and keep one. So that's the Z table, right? The standard normal is what we are having here. So it's just another normal distribution, one that is made famous because it's standardized. The mean is always 0, the standard deviation is always 1.